Hello everyone, my name is Mike, and in this series of videos I have 10 techniques that I'm going to share with you for improving your group delay measurements on frequency converting devices that have an embedded local oscillator. So by this I'm talking about devices such as this MyTech satellite block down converter, which takes a 20 gigahertz signal into the back, frequency converts it down to about 1 gigahertz using an embedded local oscillator operating at 18.75 gigahertz. So this is the type of device that I want to measure, and in particular, in this series of videos, I'm focused on measuring the group delay of this device. And I'm going to share 10 ways to improve that measurement. And of course, for these measurements, I'm going to use the Rohde Schwarz ZNA vector network analyzer. This is an analyzer that we introduced about 1 year ago that was designed specifically for making measurements on frequency converting devices. So it's ideal and optimized for this type of application. And in particular, I'm going to use the option called K9, which is our two-tone technique for measuring group delay, to do these measurements. This option has been around for a while, and it's described in application note 1EZ81. So all the details that you need to know about this particular option for measuring group delay are in that application note, including the equations and the things you can do to optimize the setup. But we don't want to read an application note right now. We want to watch videos instead. That's why I'm going to go through the 10 different ways that you can improve your measurement results in this video or in this series of videos. So let's get started, I guess. In this video, I'm going to cover my second idea for improving your measurement results, which is to select the optimal combining method for creating your two-tone signal. Now, in the Rohde Schwarz ZNA, we have 4 different ways for you to create a two-tone signal, and each way has its own advantages and drawbacks. So, in particular, when I'm picking my method for creating a two-tone signal, I want to worry about 3 different things. The first thing that I worry about is, am I adding loss after the coupler of the network analyzer? If I combine my signal with a combiner external to the instrument, I will add loss after the coupler, and that makes it harder for me to measure things like input return loss. So I worry about loss and where that loss is located. Number 2 in my list of things to worry about is, how do I measure the phase of the two tones? Depending on where I do the combining, it changes where the network analyzer can get at the two tones to measure their phase. Now, one method, if I use an external combiner, means that each tone needs to be measured with its own reflectometer and its own reference receiver. That means, for example, that tone 1 is measured with port 1's receiver and tone 2 is measured with port 3's receiver. And in that case, I have 2 different coherent receivers measuring the phase of 2 different tones. Now that'll work, and it does work, but it does mean there's 2 different sets of hardware making the measurement, and no matter what, that's not going to be quite as good as if I combine the 2 tones and run them to one receiver. One receiver making the measurement of both tones at the same time will always reduce the phase variation a little bit more than using 2 receivers. So that's another consideration that I need to take into account. The third thing that I want to take into account is, how often do I need to make this two-tone measurement versus the other measurements that I'm making? Do I need to add this combiner and then take it away and then add it and take it away all the time? Or is my setup predominantly always making measurements with two-tone signals and I can just leave the combiner in place? If I need to take it away a lot, then it might be nice to have the internal option for the network analyzer, which will automatically switch the combiner into the path when needed and take it out when we're not using it. So these are the things that I want to consider as I select the optimal way to create the two-tone signal. Now, let's take a look at the user interface and see what it looks like as I go through the process. So again, I start from a preset, and let's just say I was going to set up this frequency converting group delay measurement from scratch. Then, as you saw in the last video, I go to measure, I select mixer parameters, two-tone group delay, set up frequency converting measurement. Now, in the last video, I took the default settings everywhere I could, but here I'm going to start by optimizing this section of the setup dialog. In this section, this is where we select how we're going to create the two-tone signal. And if I click on this button, it opens up a dialog box where I will have 3 or 4 choices. So in this particular instrument, I have 3 choices because I don't have the internal combiner option, but if you purchase that option, then you will see 4 choices in this list. Let's go through them one at a time. The first choice is to use an external combiner. This is what I did in the first video. And of course, here's a picture of my setup using the external combiner. I just take the outputs of the two ports, run them to a combining element, and then the output of the combining element goes to my device under test, which is represented by this connector right here. So this is what we already did. This has the drawback of adding loss after the couplers of the ports. So this makes it a little harder to measure return loss of the device under test. And that's one of the drawbacks. And the second drawback is, as I mentioned, this relies on port 3 using this reference receiver to measure the phase of the one tone, and port 1 using this reference receiver to measure the phase of the other tone. So I have two different hardware receivers. They are coherent, but two different hardware receivers making the measurements of the phase of the tones. And that's not quite as good as if I could combine the tones and use one receiver to make the measurement. So two drawbacks of this approach, but of course, this approach is very cost effective, very easy to understand, very easy to use. So let's look at option number 2. Option number 2 is really similar, but we take advantage of the B16 direct receiver access option, which means that I can get at these individual connector locations. So now I can take my combiner and I can take the output signal of this port 1 right here, and run it to one arm of the combiner. And I could take the output signal of port 2 from here and run it to the combiner, or from the main port. Either way, and then I get the two tones combined, and then I take the combined signal and I run it back into the port 1 source in connector so it can pass through the port 1 coupler. So this has two advantages, as I mentioned. It gets rid of the loss after the coupler, so I have better directivity and better ability to measure return loss of my device under test, and it allows both tones to pass by the one receiver, the reference receiver on port 1. So now a single receiver can measure the phase of the two tones, and this will be a little bit better than the previous way. So here's a picture of what it looks like if we do this measurement, and we're going to compare the results of both measurements in just a moment. So first, let's look at option number 3. Option 3 is to use the coupler as a combiner. Now what this means, when we're creating a two-tone signal by combining ports 1 and 3, it means that the coupler on port 3 is no longer needed by the network analyzer because the source is being routed to port 1 to create a two-tone signal. So in that case, we could reuse the coupler on port 3 as the combining element. We can run one of the two tones through the main arm of the coupler, and the other's tone can go through the coupled arm of the coupler, and the combined output can be run back into port 1. And that's exactly what happens here. We take the source out from port 1, and we run it through the main arm of the coupler. We take the source out of port 2, we run it through the coupled arm of the coupler, and then we take the combined two-tone signal and run it back into port 1 so it can pass through the port 1 main arm of the coupler, and the reference receiver in port 1 can monitor the two-tone signal. So this gives us all the advantages of the previous technique, but we reuse the coupler that's already in the instrument and sitting idle otherwise. So this option is very attractive because you just add two semi-rigid cables to the front panel of the instrument. And it looks like this when you do it. And this is the technique that I use every time I can. So in fact, my goal is to primarily leave these cables on all the time. Most of the time I'm measuring frequency converters, so I'm measuring either group delay or intermodulation, or sometimes I'm measuring amplifiers where I want to measure intermodulation, so I take advantage of this two-tone setup nearly all the time. And rarely do I have to disconnect these things to measure a 4-port device. Instead, I'm measuring amplifiers and frequency converters. So a very attractive option. Now, option number 4, which I do not have in this instrument, but it'd be a fourth choice here, is to switch in a combiner using mechanical relays inside the instrument, and then you can switch that in and out as needed. So the diagram looks like this. In the overall, I have 4 choices, so the diagram would look like this fourth one right here. So this is very handy if you need to switch back and forth between creating a two-tone signal and then creating a single-ended port for other purposes. So if you have to switch a lot, then this option makes a lot of sense. If you switch rarely, then perhaps the semi-rigid cables, which are option Z9, maybe that looks more cost-effective and attractive to you. So 4 ways to do the measurement. So what we're going to do now is go through the 4 different ways. We're going to set up the channel, and we're going to measure, we're going to calibrate and measure group delay with each way, and we're going to compare the results. Now, actually the 3 ways, because I only have 3 options. So now, because I have to reconfigure the test set, and recalibrate and measure each time. What we're going to do is go through the process, and then I'm going to save the trace on the screen as a memory trace, and then reconfigure for the next one and create and save another memory trace, and so on, so that you can see the results of each technique as we go. Okay, so let's start with number one. I'm going to do this fairly quickly because we saw it in the first video how to do the setup, but let's just do it and go real fast. So 19 gigahertz to 21 gigahertz using port 4 as the LO, set to 18.75 gigahertz and 10 dBm of power. Again, using the external coupler option, same thing we did in the first video. Let's say OK. We go to a two-tone group delay measurement and set the calibration mixer to 190 picoseconds and do a calibration. All right. Now that I'm calibrated, I'm going to connect to the device under test and then save that to a memory trace. Auto scale, and let's go a little closer. So this is what it looks like, same thing we saw in the first video. So this is method number one, using an external combiner to measure the two-tone group delay of the frequency converting device. So let's save this to memory, and then you wait here. I'm going to reconfigure the test set. I'm going to recalibrate with the reconfigured test set, and I'm going to show you the second trace using technique number two, which is to take the two-tone signal that's combined and run it back into the source in port of the port 1 coupler. Okay, be right back in a moment. Okay, I'm back. That was quicker than I thought. So I've reconfigured the test port. It looks like this. Okay, so now I'm using the external combiner with the B16 option, and then I recalibrated the channel and then connected to the device under test. So I am now making the measurement with this green trace, and when compared to this blue trace, it looks just a bit different. So can we argue that one trace is better than the other? Well, perhaps. It looks a little bit better on the green trace. I'm a little biased here because I already explained that I think this process using one receiver would be a little more accurate than using two receivers. So we could argue that it's a little bit better. Let's put on the trace statistics and take a closer look. So trace 1, trace config. Let's go to the trace statistics, min, max, peak to peak, mean, standard deviation, pick an evaluation range 1, which goes from 19.8 gigahertz to 20.2 gigahertz, and turn on those range limits. And then let's do the same thing for the second trace, which is stored in memory. Okay, and also want to use range 1 on it. And now let's take a look at the peak to peak. So on this second trace where I used the external combiner, but then I ran the signal back into port 1 so that both the tones pass by a single receiver. In this trace, I do have lower peak-to-peak variation than I had in the previous measurement, and the standard deviation is also a bit lower. So this green trace truly is slightly better than the blue trace. So, and the logical reason for this is that I'm combining the signal and then passing by a single receiver. So I would say this is a little bit better. Now, there's a third option that I can pursue. Right now, the current option is that I did this, combining like this, but there is a third choice, which is to use the coupler as a combiner. So I will set this up next. I will calibrate the channel, and then I will connect back to the device under test so we can take a look at the third choice. Okay, be right back. Okay, I'm back. Again, quicker than I thought. So now I'm looking at the third technique, which is using the coupler as a combiner. So let's just take a quick look here. So this configuration right here, which looks like this. And in this technique now, I'm creating the two-tone signal using the port 3 coupler, which was otherwise sitting idle. I've calibrated and then I connected the device under test. So this is what the measurement results look like. And now I would say they're just a little bit worse than what we had before. And I'll have to tell you that in video number 3, we're going to figure out why that is. And let's say a little hint coming up is it involves power levels. So the fact that we're using this coupler as a combiner does not give us equal power tones. So that's what's causing a little bit of degradation here, but it's an easy thing to address, and that's what I will cover in the third video. So in summary now, if I had the internal combiner, the results would look a lot like what I saw with the external combiner being routed back into the source port of the VNA. So I have 4 options. These are the 4 options again. 3 of these options combine the signals before the coupler on the port 1. So a single receiver can measure the 2 tones and their phase delta, and also there's no loss after the coupler, which makes it harder for us to measure return loss. So these 3 options are the best options with respect to making the measurement in terms of allowing us the most accuracy and the most flexibility. And then this option is the external combiner option is the one that we would use if, well, let's say we don't have the ability to do anything else, or we just have to pick an option really quickly. So that's my conclusion in the second video. Picking the optimal way to create your two-tone signal is number 2 on my 10 techniques for improving your group delay measurement. Again, watch video 3 where I talk about optimizing power levels, and we're going to make that technique using the coupler as a combiner just as effective as the other techniques. Okay, I will see you then.